So in this screencast, we're going to talk about food and consumer energy. We've been talking up until this point about energy and thermodynamics and how much energy is involved in certain chemical reactions. So this is sort of like a touchy-feely, real-world application concept of food and energy. Sort of just to wrap up the whole thermodynamics discussion. So two kinds of energy that we've talked about: chemical energy and chemical reactions. There are two other kinds of sort of energy that humans have a real life connection to. And the first is food. So one of the things that we do a lot of as humans and as animals is convert glucose into, and we breathe oxygen to form carbon dioxide and water. And you've seen many chemical equations at this point, and you know what a reasonable delta H of reaction is. So this delta H of minus 2,803 kilojoules per mole, that's an awfully large number compared to any other reactions we've really talked about. And that's sort of important. But, glucose, which is, simplest sugar, does give us a lot of energy. That's why we eat sugar. That's why we eat Snickers bars. That's why we eat strawberries. It gives us a lot of energy. Your body takes a lot of energy to do all those things, to breathe, to keep your heart pumping, keep your blood flowing, all those cells, all that energy. We need a lot of energy to just honestly stay alive. So we need to eat a lot of glucose. We eat sugar. A bottle of Mountain Dew has what, 60 grams of sugar, most of which is glucose. 60 grams of glucose. It's quite a bit of glucose, and that's a lot of energy. Now, fats, which is, we also get energy from fats, and fats are much more complex. Here is tryptine, I don't know, but it's one of the many kinds of fats that we eat. Think oils are fats, and to just the amount of energy, if you see here 2 moles of this tryptine, and notice it's a very long, complex thing, but it undergoes the same sort of combustion, if you will, the same sort of reaction by our body. It breaks it down. We break down that fat, and after many different steps, using again the oxygen we breathe, breaks it again down to carbon dioxide and water. So it's the same sort of products as when we're breaking down glucose, but obviously this is a much larger molecule. But as you can tell, for the same number on a per mole basis, the amount of energy is much more. This is 75,000 kilojoules per mole, which is a lot. So generally, fats and glucose is a carbohydrate. In general, fats give us about twice as much energy as carbohydrates. And this is really why you have fat stores in your body, such that it's a storage of energy. And so when you need energy, it burns the fat. It's such that if you don't have food for a while, you start burning fat. That's sort of like the whole survival thing. That's why we eat. But our bodies are built such that you can go a couple of days without eating any food and you won't die, because you just start chewing your fat. Now, so that's sort of energy coming from food. What about fuel, or what about energy from consumer? Right? So we are an energy-rich society, and we have lots of different sources of energy, and we've had sources of energy over the years. Some of the more natural, or the most notable ones that we've done over the course of history, is wood, and wood gives us about 18 kilojoules per gram, which isn't a whole lot, but the great thing about wood is that it's cheap. Just go out to the forest and chop down the tree and burn it, and it gives us energy. Once we started having so many people on the planet, though, it started, we needed more energy, and we can't chop down all of the forests. So we started pulling stuff out of the ground. So coal gives us almost twice as much energy per gram, gives us about 31 kilojoules per gram. And the great thing about coal is that it's from underground, so you can't really see it. So it's not like when you're chopping down forests, you can see that, and it's bad, and it looks bad, and so we don't like doing that. Whereas coal, we pull it from out of the ground, and nobody notices it. Of course, the problem with coal is that it's very dirty. It's got a lot of impurities in it, and you get the black smog, and of course mining it, you get death from black lung disease and stuff like that. but it's dirt cheap. It's very, very cheap to pull it out of the ground, and that's why most of the energy in the United States still comes from coal-fired power plants. Gasoline, even more energy, 48 kilojoules per gram. Also, that's a lot of energy per gram. Same sort of problem in that we have the impurities, and it's an oil-based. Then natural gas, we pull that from out of the ground. Natural gas is actually in the pockets of the gas pockets above oil reserves under the ground. So when gasoline comes from oil, and when we're mining the oil and pulling the oil out of the ground, there's also gas coming off the top. Natural gas gives about the same amount of energy per gram as gasoline does. Natural gas is much more clean burning. Natural gas, because it's a gas, purifying gases is really easy. Purifying liquids is not so much. Purifying solids is almost impossible, which is why coal is filled with pollutants. It's very difficult to sort of like purify it, so we don't put so much pollution in. Liquids are a little bit easier to purify, but it's still tough and expensive. We can make gasoline such that it burns perfectly clean, and there's no pollution that comes out of the back of your car. The problem is that your gasoline would be, about $100 a gallon if we would do that. Natural gas, because it's a gas, we can purify it, and you can actually make it such that natural gas is a very clean burning fuel, and that's why we do natural gas in houses. Gas ovens and gas stoves are natural gas, and obviously they don't put out a lot of pollution because we have them in our homes, and it's perfectly safe because it's clean burning, whereas we couldn't have a gasoline fired stove. That would just be bad, and we're certainly not going to cook in a coal-fired stove. That'd be gross. Then there's hydrogen, and hydrogen is, and these four are called fossil fuels because the reason why they're called, the name comes from most of, like coal and gasoline and natural gas are dead animals and dead plants, and so these are things that are dead, and I guess the wood is dead once we chop it down and put it into the fireplace. So those are fossil fuels. Now hydrogen is a wonderful hydrogen economy that people have talked about for years about putting it on. Hydrogen is very, very energy efficient. It gives 142 kilojoules per gram. Way, way more energy than any of these. And hydrogen is perfectly clean burning. When you burn hydrogen, it burns cleanly and forms pure water. That's it. Not even any carbon dioxide. Just hydrogen mixing with oxygen in the air forms pure, clean water. And so it's about the cleanest fuel that is humanly possible. And it gives us so much energy. So why don't we just burn hydrogen and use that as our energy source? Well, we could, but there's two problems. The first problem is that hydrogen can't be mined. It's not like, we'll just go underground and find the hydrogen gas, like natural gas or gasoline or coal. It's not naturally occurring. There's very little pure hydrogen in the world. We can make hydrogen. It's very easy to make hydrogen. We do it often. What we do is we take water and we dump a bunch of electricity into it, and the water turns into hydrogen gas and oxygen gas. Problem is that we need the energy to sort of put into the water to make the hydrogen. So hydrogen is all well and good, but the problem is that it's a fuel that has to be made. The reason why these are all good sources of energy is I don't have to make the wood. Mother Nature makes the wood and the coal and the gasoline and the natural gas. I just have to pull it out of the ground or chop it down. Whereas hydrogen has to be synthesized. That's the first problem. The second problem is it's kind of dangerous. It's a gas, and it's very explosive, and if you've ever heard of a thing called the Hindenburg, that's what happens when you have a large pocket of hydrogen gas that gets near a flammable, near a flame, and you burn that hydrogen very, very quickly, and so you get really nasty explosions. So it's kind of unsafe for that reason. Renewable energies, of course, are all wonderful and great, and except they all have their own flaws. So there's lots of talk about, solar power. Solar power is this wonderful, awesome thing. Well, the problem with solar is that it's very inefficient. Only about 10 to 15% of the amount of energy, solar energy that hits the solar panel is actually converted into electricity. But it's free. The other problem with solar is that it's weather dependent. When it's a cloudy day, there's not as many photons coming from the sun hitting the solar panel, so you don't get as much energy. And the problem with consumer energy is that as soon as I turn on the switch, I need the energy. There can't be sort of a delay. So there always has to be energy being put down the pipe. These, coal-fired power plants, gas-fired power plants, natural gas-fired power plants are constantly on, and there's no sort of lull. And we can, if we need more energy, we can just, put more coal on the fire, if you will. Whereas with solar, it's just like, okay, so I've tapped into the solar panel, and it's just like, okay, so it's the middle of the day, and I've got all my air conditioners running. What happens when you have all this energy draw? What happens when the sun goes behind a cloud? All of a sudden, the amount of energy drops because the solar panels just aren't getting as much energy, and then all of a sudden, you don't have anywhere near as much energy to put down the pipe for the consumers, and everybody's air conditioner goes off. So, that's a problem. Hydroelectric, so dams. Dams are good and bad. They're good in that they provide a constant amount of power because you get the big lake behind the turbines that are always spinning, so it's not weather dependent. You have a hydroelectric plant or a dam will put out the same amount of energy 24/7 if you want it to. You don't have to adjust anything. It will just churn out the same amount of energy all day long, day, night, storm, whatever, because of how it's sort of set up. The problem is with hydroelectric dams is it's sort of localized. You can only do it on like big rivers. And the other thing is it's horribly expensive. I mean, it'll take about 20 or 30 years to sort of like pay off the cost of building the original dam. So it's very expensive. You also have a problem of you totally wreck the local ecosystem. You screw with all the poor fishies who, spend their lives going up and down this river for spawning and such, and all of a sudden you put a dam in the way and they can't go to where they're supposed to go. So, it's really bad for the fishies. Wind power also gets a lot of press. It is also weather dependent. And, if it's not windy, you're not generating any power. And some people don't like it because it's unsightly. And that, I don't want to, you're ruining my beautiful view. And so that's why that's why a lot of politicians and rich people fight against wind power, is because, it's visually unappealing. And then there's geothermal, which is fun and cool and exciting. Basically, all of these fossil fuels, what we're doing is we're burning fuel to generate a fire that heats up water, which makes steam, which passes by a turbine, which generates electricity. The way geothermal sort of energy is basically we're going and finding places like in Iceland or even in San Francisco, in the California area, where there's sort of cracks in the ground where you've got like steam literally coming up from the earth because there's like a hot spot or whatever, and you basically just take the steam that's coming out from the ground and you take that hot air and hot water and have it turn into steam and have that steam go by a turbine and generate electricity. And the great thing about geothermal is it's essentially free. You don't even have to do anything. You're basically just sort of like putting a cap over the steam that's coming out of the ground anyway and pushing it by the turbine. The only problem is that there's only a couple places on the planet where there's enough heat coming out of the ground for it to be worth it. So like Iceland, for example, like 80-90% of their energy is geothermal. 80-90% of their energy is completely free because it's literally just sort of coming out of the ground and they're just capturing it. But again, that only works in places like Iceland where you got steam and you're like on near active volcanoes. It's another good place for it, but most of us don't live near active volcanoes, so it doesn't really help us that much. So again, this was just sort of want to give you make you a little bit more of an informed consumer, and as a scientist, you are going to be looked up to by your fellow citizens as, hey, he's a scientist, he's really smart, and they want to ask you about, I'm hearing all this stuff about, why is wind power so great and why is it so bad? And they're going to ask you, and now you know a little bit more.